Context engineering, the evolution beyond prompt engineering. The great paradigm shift from prompts to environments. We're witnessing a fundamental transformation in how we build AI systems. While the industry spent years perfecting prompt engineering, crafting the perfect instructions to get desired outputs, production reality has revealed a deeper truth. The quality of AI responses depends less on perfect prompts and more on the entire information environment the agent operates within. This diagram illustrates the architecture of context engineering, a systematic approach to designing everything an AI agent sees, processes, and remembers before generating responses. It's the difference between asking a human expert a question in an empty room versus providing them with a fully equipped research library, relevant documents, conversation history, and specialized tools. The context engineering architecture, an information ecosystem. The user agent core loop, steps 1 and 2. The journey begins with user input, step 1, but unlike traditional prompt engineering, the input immediately enters a sophisticated processing pipeline. The agent, step 2, isn't just receiving raw user queries, it's operating within a carefully crafted information environment that has been systematically designed for optimal decision-making. This represents a fundamental shift from the garbage in, garbage out mentality to context in, intelligence out. The agent's capability is directly proportional to the quality and relevance of its operational context. The knowledge retrieval engine, step 3. RAG, Retrieval Augmented Generation, sits at the heart of modern context engineering, performing vector searches to identify relevant information from vast knowledge bases. But this isn't just about dumping search results into the prompt, it's about intelligently curating information that enhances rather than overwhelming the agent's reasoning process. The RAG system acts as an intelligent librarian, not just finding information, but understanding what information is most relevant for the specific reasoning task at hand. This requires sophisticated understanding of query intent, information hierarchies, and contextual relevance. The tool integration layer, step 4. Action tools represent the agent's hands in the digital world, capabilities to execute code, access databases, call APIs, perform calculations, and interact with external systems. Context engineering ensures these tools are presented with clear schemas, usage examples, and appropriate access controls. The genius of this approach is that tools aren't just available, they're contextually relevant. The agent understands not just what tools exist, but when and how to use them based on the current conversational and task context. The prompt orchestration. The prompt in context engineering is no longer a carefully crafted static instruction, it's a dynamically assembled context window that combines multiple information types: user input, purple, tool schemas, green, RAG context, blue, user information, white, agent reasoning, like blue, and chat history, yellow. This multi-layered prompt construction represents the culmination of context engineering, a systematically designed information environment that provides the agent with everything needed for intelligent reasoning and response generation. The response generation, step 6. The answer emerges not from prompt wizardry, but from the agent's ability to reason across a rich, well-structured information context. The quality of responses is directly correlated with the quality of context engineering that preceded it. The memory architecture, steps 7 and 8. Short-term memory, the working context. Short-term memory represents the agent's immediate working context, the conversation history, current task state, and active information threads. This isn't just a chat log, it's a curated representation of the conversational and reasoning context that maintains coherence across interactions. The color coding reveals the sophisticated information layering. User inputs, tool interactions, retrieved knowledge, and reasoning threads are all maintained in a structured way that enables the agent to understand not just what was said, but the contextual significance of each interaction. Long-term memory, the persistent intelligence. Long-term memory systems using MCP servers and databases represent the agent's persistent knowledge and experience accumulation. This goes beyond simple storage. It's about creating searchable, relational knowledge structures that can be intelligently retrieved and applied to new situations. The add to memory function, step 8, represents one of context engineering's most critical capabilities, the ability to learn and accumulate context over time. This transforms agents from stateless answering systems into persistent learning entities that improve through experience. The context engineering methodology, beyond prompt crafting. Static versus dynamic context components. Static components form the foundation of the agent's operational environment. System instructions, tool definitions, domain knowledge, specialized information relevant to the agent's area of expertise. Dynamic components adapt to each interaction. User input, the immediate query or request, recent conversation, contextually relevant interaction history, retrieved documents, information pulled from knowledge bases based on current needs, and tool outputs, results from previous tool executions that inform current reasoning. The three-layer memory architecture. Context window, immediate. The agent's working memory for the current interaction carefully curated to include only the most relevant information for immediate reasoning. Session memory, short-term, conversation state and task continuity that persists across multiple interactions within a session. Persistent memory, accumulated knowledge, user preferences, and learned patterns that survive across sessions and enable true personalization and expertise development. Context failures, the hidden killers of AI systems. Context poisoning occurs when irrelevant, outdated, or incorrect information enters the agent's reasoning environment. Unlike hallucinations generated by the model, context poisoning comes from external sources, bad RAG retrievals, outdated knowledge bases, or corrupted memory systems. The solution isn't just better filtering, it's building context validation systems that can assess information quality, relevance, and consistency before it reaches the agent's reasoning process. Context overload. The information paralysis problem. Throwing everything available at an AI agent doesn't improve performance, it degrades it. Context overload occurs when agents receive too much information, creating decision paralysis and reducing response quality. Effective context engineering implements intelligent information hierarchies, relevance scoring, and dynamic context pruning to ensure agents receive optimal rather than maximal information. Context clash, when information contradicts itself. Context clash happens when different information sources provide contradictory data, confusing the agent's reasoning process. This is particularly problematic in enterprise environments where multiple knowledge sources may have inconsistent or overlapping information. Advanced context engineering includes conflict detection, source authority weighting, and reasoning frameworks that can handle uncertainty and contradictory information gracefully. The production reality: why context engineering matters. Reliability, from demos to dependable systems. Prompt-engineered systems often work brilliantly in controlled demonstrations, but fail unpredictably in production. Context-engineered systems provide consistent performance because they operate within systematically designed information environments rather than relying on prompt craftsmanship. Scalability, beyond individual conversations. Context engineering enables agents that improve over time, learn from interactions, and build institutional knowledge. This transforms AI from a series of isolated interactions into continuous learning systems that become more valuable with use. Maintainability, systematic versus ad hoc approaches. Prompt engineering often devolves into collections of special cases and edge case handling. Context engineering provides systematic frameworks for managing agent behavior, knowledge integration, and capability evolution. The technical implementation, architecture for intelligence. Vector database integration. Modern context engineering requires sophisticated vector database implementations that can perform semantic search, maintain embeddings consistency, and handle dynamic knowledge updates without degrading retrieval quality. Memory management systems. Effective memory systems must balance retention with forgetting, personalization with privacy, and accuracy with adaptability. This requires sophisticated architectures that can maintain multiple memory layers with different retention policies and access patterns. Tool orchestration frameworks. Context engineering demands tool systems that provide not just functionality, but contextual intelligence about when and how tools should be used. This includes dependency management, error handling, and capability composition. The organizational implications, beyond technical implementation. Team structure evolution. Context engineering requires different skill sets than prompt engineering. Teams need expertise in information architecture, knowledge management, and systems design rather than just linguistic craftsmanship. Quality assurance methodologies. Testing context-engineered systems requires evaluating entire information environments, not just prompt response pairs. This demands new QA methodologies that can assess context quality, information consistency, and reasoning reliability. Operational monitoring. Production context engineering requires monitoring information quality, retrieval performance, memory consistency, and context utilization patterns. Traditional AI monitoring focused on model performance. Context engineering monitoring focuses on information environment health. The future landscape, where context engineering leads. Autonomous learning systems. Context engineering enables agents that don't just respond to queries, but actively learn from their environment, building expertise over time and adapting to changing requirements without explicit retraining. Enterprise knowledge synthesis. Well-engineered context systems can transform organizational knowledge from static repositories into dynamic intelligence systems that actively support decision-making and knowledge work. Personalized intelligence. Context engineering makes true personalization possible, not just customized responses, but personalized reasoning that adapts to individual users' expertise levels, preferences, and working styles. The strategic advantage, context as competitive moat. Organizations that master context engineering will have fundamental advantages over those still focused on prompt optimization. Intelligence amplification.